coming. Electronic Solutions. I actually one of the absent engineers here. This is Austin Swanberg.
Hi.
So I'm going to let Austin's one of our other applications. I'm going to let him take it.
Hi, everyone. Thanks for coming. Today, we're going to talk about Omron's mobile robots and kind of their advantages, their different models that they have, as well as a lot of the different features that we can do with them. I'm going to start off by talking about who we are, Mechatronic Solutions as a company. So we are a Omron distributor. We do kind of all automation, robotics, controls, PLCs, stuff like that. Most of our staff are engineers, automation specialists, or technicians. We have a team of 5 apps engineers here that are all kind of cross-trained on everything to be able to help out all our customers with any other projects. So one of the advantages of Omron and their mobile robots is that Omron offers kind of a full suite of automation. So besides their robots, they also do controls, vision, HMIs, and a lot, as well as safety. And that is all kind of meant to pair very well together. They make it super easy to control a robot using their PLC, get it up and running. You can kind of do everything that you need to through one software versus having to kind of piece everything together. So Omron has a couple lines. Their mobile robots are called the LDs, the MDs, the HDs. We'll go over that in a second. They are AMRs. So one of the big things is you might have heard the term AGV in the past. So what is an AGV versus an AMR? An AGV is an automatic guided vehicle or automated guided vehicle. And what it does is it moves around your facility, but it's looking for kind of different features that you have to set up in your building, whether that's magnetic tape on the ground, sensors that it's constantly locating off of. And it basically follows pretty strict paths on your floor. If you want anything to change, you have to add new magnetic tape, new sensors, all of that. In AMR, which is an autonomous mobile robot, which is what Omron's mobile robots are considered, it is a little different. Instead, you will just create a map, and then the robot kind of has full autonomy to do whatever it needs to get from one location to the other. So it doesn't have to follow a set path. It can navigate around features, whereas an AGV might stop if something is on its path. The LDs can navigate around it and kind of take whatever path they need. And the nice thing is you can run these robots kind of as a mix. So you can set up the AMR to run as an AGV if there's a certain area of your building that you don't want it to kind of deviate from. But we'll go over that in a little bit. Omron essentially has kind of 4 different models or 4 different form factors for their mobile robots. The smallest ones are going to be the LD60 and the LD90, which you'll see here. Those have the same form factor. That 60 and 90, that is the payload capacity of the robot. So these robots can carry 60 kilograms or 90. Essentially, they're just geared slightly different so that they have different payloads. The next largest size you'll see over here is the LD250. So 250 kilograms, slightly larger form factor, and kind of a slightly different panels on it. Their next largest is going to be their MD series. I like to think of it as basically light duty, medium duty, heavy duty. So their MD is kind of their middle of the road. They have a 650 and a 900 kilogram. So these are meant for carrying pallets around warehouses, stuff like that. And then on the largest end, they have the HD 1500. So this is a 1500 kilogram robot meant for very, very large applications and moving kind of large pallets, car bodies, stuff like that around a building. One thing I do want to point out is that the larger robots, the MD and the HDs, do actually have a Omron PLC as well as a safety PLC on board, whereas the LDs have to basically communicate to an external PLC. The MDs and the HDs have that built in. It gives you the option to add safety sensors and different options to the topper with just a little bit more ease. So looking at the LD90, I'll point out a couple of features. So all of these robots, their main sensors that they're going to be using is going to be this one right here. That's an Omron area scanner. So it's a LiDAR that's basically spinning extremely fast, and it's taking that reading from the light and building an environment around it. That's the robot's main navigation laser. It might be kind of hard to see, but there's actually another sensor. It is called the low front laser. What that does is it's a smaller LiDAR that's actually angled slightly towards the ground, and it uses that in order to pick up any objects that might have fallen in front of the robot or are just placed on the ground to make sure it doesn't run over them that the main laser might not see. That main laser essentially scans a plane that's 7.5 inches off the ground. So anything below that or above it, it won't see. It only looks at that. So that low laser is just to help make sure it doesn't run anything over. On the back of these robots, you'll see there is a sonar array of 4 different sonars that it will use to detect any objects or obstacles behind it. These robots, because its main laser is that LiDAR, it has a 270-degree view. It likes to move forward instead of back because that LiDAR gives it a lot more information than the actual sonar does. You'll see these robots are kind of designed to be able to spin in place. So if it needs to move, you'll see it turn and continue to move straight instead of moving backwards or anything like that. We do have light bars on the side that give you kind of an indication of the robot status, whether it's charging or not. So green is charging. It will actually fill up that light bar depending on how charged the battery is. So from a distance, you can look at the LD and see, okay, is it almost dead? Is it fully charged? What the status is. Under normal operation, it'll be blue. If the robot ever gets lost, it'll show that by turning yellow, and then if it gets e-stopped, it will turn red. We also have internally, you can't really, there it's covered, but there is a power connection as well as I/O built into the robot. So if you have sensors, outputs, if you want to run a conveyor or anything off of it, you can power it directly off of the robot. All of their LD series use the same battery. It's a lithium-ion battery that it is a smart battery, so it prevents you from overcharging it or damaging it from just letting it sit on the charger. It makes sure that all of your cells are evenly charged just to kind of prolong that life of the battery. They are interchangeable between the 90, the 60, and the 250. On this one, it's a little hard to see with the topper, but essentially the same as this. There is an operator panel on the top. This will give you any any statuses of the robots. It'll tell you what job it's running, what goal it's going to. It'll tell you its battery charge, as well as how well its signal is to your network, as well as giving you a power on and off, a brake release so that you can move it around, as well as an additional e-stop. The one thing that the LD90 and the 60 has that the other models don't is going to be this front bumper. It'll move. If anything does end up ever hitting it, it'll essentially just e-stop the robot. But the robot, using all its other sensors, will essentially prevent anything from ever triggering that. Sorry, before I move on. One thing about these is all of the panels are actually just magnetic. So it makes getting to the internals of the robot very easy if you ever need to address that or look at the main laser. Switching over to the 250, a lot of its features are pretty similar. It still uses that same LiDAR that the 90 and the 60 uses, the Omron area scanner. It also has that low laser that it uses for detecting obstacles. One of the big differences, though, is that the 250, instead of sonar in the back, it actually uses an array of 12 time-of-flight sensors to essentially do the same thing, but you just kind of get a little more precise reading using those 12 sensors versus the 4 sonar array. The 250 also changes all of its panels from being kind of plastic exoskeleton to metal panels. So it's kind of meant for a more industrial warehouse kind of environment. It has panels that can take a little bit more of a beating. Those ones are not magnetic. You'll see that they actually do have bolts that hold them on in place. With the 250, you also get the addition of 2 e-stops, one on each side by the light ring, just in case you need to e-stop it. In that internal power and I/O, there also is an additional e-stop circuit if you ever do need it. The 250 also has the same identical operator panel as well as the light rings. It uses the same battery as the 90 and the 60, and then of course we have our 2 antennas in the back that connect it to a wireless network. Looking at the larger models, so the MDs, this is Omron's their newest line that just came out. It was kind of meant to bridge the gap between the LDs and the HD and offer kind of a middle ground for it. One big difference that the MDs have, and as well as the HDs compared to the LD, is that this actually has 2 LiDARs. So instead of one laser that is in the middle or in the front centered and gives you 270 degrees, this one actually has a laser here as well as in that corner, kind of kitty corner to each other, and that will actually give you a full 360-degree view of the robot. With the MDs and the HDs, you'll see that this robot actually doesn't really have a preferred front and back. So if it needs to, it'll just go backwards, whereas the LDs, like I mentioned, have to spin. It has e-stops on the sides. This one does have magnetic covers on the side for easy access. It gives you an additional front LED for the status. You still get your low laser. And then, like I mentioned, this one also has that built-in PLC and safety PLC for any, as well as their power and I/O for anything that you want to add to the robot. The HD is very similar to the MD. It's just slightly larger. It again has the 2 LiDARs kitty corner to each other, e-stops, the safety rings, as well as that safety PLC. One thing that the LiDAR will do is it will actually kind of dynamically adjust those safety zones for the robot as it's moving. So it knows that when the robot is moving faster, it has more momentum behind it. It's going to take longer to stop, be able to slow down whatever load it's carrying. So it will actually increase that buffer zone that it has as a safety distance for the robot, depending on the speed. All of this is interchangeable. You can set the distances and everything you want through the software, but it is kind of a dynamic adjustment. All of the robots have the option for some additional hardware and software features. One hardware feature that you can get is you can have side-mounted lasers that are actually, it's the same laser as what that low laser is, but it's mounted vertically on the side of the robot instead of horizontally. And what that will do is it helps prevent the robot from going under anything that might be an overhang or something that it can't see on that 7.5 inches off the ground. Take a table, for example. It might see, at 7.5 inches, it might see 2 posts for the legs, but it has no idea what that tabletop looks like. So if you didn't kind of account for that in your map, it might see in between those 2 legs as a viable path. So what those side lasers do is it basically will just scan and see the top of the table as an obstacle and prevent it from going under it. And then those can be added to the 250s, the 90s, the 60s. One thing that they also add, it's shown here, is what Omron calls acuity. So Omron uses a map that it matches what the LiDAR is seeing to kind of a reference map in order to navigate. All of the robots also have encoders built into the wheels, and it uses both of those to kind of figure out where it's going. Because it has the encoders, if it ever loses localization from the map itself, it can still navigate because it's relying on those encoders. Say you have a floor where it's kind of dynamically changing, where you might have a pallet somewhere and then the next day it's completely different. The robot can't use that as a reference. So instead it'll rely on the encoders. If you have a very large warehouse where maybe you don't have a lot of reference walls to look off of, or you really only have the columns in the center of the floor, if your floor is very dynamic and your pallets are constantly changing, Omron has this option called acuity, and what it does is it actually mounts a camera to the top of the robot, and it looks at the light fixtures in your building and essentially uses the lights as a second map in order to navigate off of that, so that it's not relying just off of the encoders and the front laser. In those larger warehouses or areas with very dynamic floors or just large open spots, is a really good option just to make sure that your robot is always able to find its location. As well as the hardware options, Omron also has a couple software options. Notably here, it's called CAPS and HAPS. So starting with CAPS, it's an acronym for Cell Alignment Positioning System. And what it does is it actually locates basically a cell off of reference points. One thing that you might use this for is if you have to dock the robot to a conveyor. You want to make sure that you can get as close to that conveyor and as repeatable as possible. This will look at maybe the conveyor legs, or maybe you build a target at the bottom of the conveyor and program that into the software. It will look for that specific reference, so whenever it gets to a goal, it will use that to redirect and kind of fine tune itself. With this, the robot's able to get down to, I think Omron quotes plus or minus 8 millimeters of precision on that. This is used a lot for parts or basically just aligning with cells. The other option is called HAPS, High Accuracy Positioning System. This is kind of more along the lines of those AGVs, where it's using magnetic tape on the ground. So this is kind of both a software and a hardware option. It actually does mount a magnetic sensor on the bottom of the robot, and then it gives you magnetic tape that you will place around just to give it a little bit more of a defined path. It can basically jump on and off this line. It doesn't need to always use it. It can use it only for the last couple feet before a goal. And then, yeah, you can see up top, if you had a cart, it essentially would use the legs of that cart as a goal. You'll see it a little bit once we get into the demos with Rowick. So before we can do anything with the robots, we essentially have to create a map so that it knows where it is, where the goals we want it to go to are, and kind of how we want it to get there. We can set up one-ways, we can give it speed limits, stuff like that. The way that Omron does this is through a software called Mobile Planner. It is a free download. Anyone can download it and be able to connect to the robot. Once we have Mobile Planner, essentially all you have to do is take this joystick, which plugs into these access panels on the side of the robot. If I press in on this, it'll pop out and give me access to a plug. There's also an Ethernet plug in this same panel that lets me connect to the robot for maintenance or any setting changes that I need to do. So with this, we can map a room and basically use that as its reference point. So if I jump out of my PowerPoint, I'm going to connect to my LD. This is Mobile Planner. Essentially, this will let you see all of your robots over here. It will let you build the map, scan a map, and add all of your features. You can see here, this is the map that the robot is currently using. But to set up a map, it's super simple. All you have to do is use that joystick, walk the robot around. So if I want to, I can come to robot and I can say map creation, and I can start a scan. As soon as I do that, on this back panel, you'll see that it is giving me, it says that it's scanning, and now it's using that LiDAR and it's creating a map and basically just building a set of reference points. All I need to do is walk it around my different paths and any kind of spots that I want the robot to navigate. On the joystick, I have a trigger that just enables the driving, as well as just this joystick that controls it. When navigating, we want to make sure that we're doing a path kind of forward and back. What will tend to happen is if you just walk one way down a hallway or one way down a corridor, you'll end up with only seeing kind of two walls of any shape, and you end up with a lot of kind of L-shaped objects in your map. So if you go the other way, you'll end up kind of completing that object. And if anyone wants to come give it a try, walking the robot around, feel free. Otherwise, all it takes is just quickly walking the robot around my building. When you map, you can actually have people walk in front of the robot. You don't have to kind of stop your normal workflow. The robot knows that if something was there when it scanned it the first time, but it wasn't there when it scanned it the second time. Or if it sees something walking, it knows that that's not a permanent object, and it ends up just deleting that from the map. Get over here just to give us kind of a full view. So now that I've walked it once, I'll just basically do the same route, but in reverse, just to give me the other side of all of those objects. Once you've created one map, you also can share that to all of your robots. You don't have to create the map per robot. There also is a goal button on the joystick. So if you're driving the robot to a specific goal that you know your map is going to need in the future, you can press that button and it'll drop it into the map, just to save you a little bit of time, or making sure that you know that that's the exact position that you wanted. So if I come back to my software and I stop scanning my map, I can come and I can open that, and we'll see here I can open my scan file. What you'll see is it actually is going to kind of show you the path that the robot takes, as well as all that information back from the LiDAR. So you'll see this is the map data it gives me. But what it's doing right now is it's comparing all of those points, and it's saying that some things look on one pass compared to another look very similar. So it is making sure that one corner that it saw matches up to another corner that's almost right in the same spot, and it gives you a cleaner version of the map. So this is that finalized map that it gave us. You can see down here, I didn't go far enough over there, so I have a couple spots that it didn't fully see. But it gives you a clean map in just a matter of minutes. Then all we have to do is add the different goals that we want. One thing to point out is notice that it actually saw those chairs out in the lobby, and we don't have too much of a wall here. That's just because it's a glass wall. Clean glass, the robot will be able to see through. Sometimes we'll have customers that basically will put a frosting just down at the robot's level, just to give it a little bit more navigation. If I want to, I can also clean this up a little bit. So if I wanted to get rid of anything over here, I can just delete those points. If I also wanted to make sure that I had a solid wall there, I can just add that. This is kind of the map, just the simple map that the robot's going to use. If I want, I can add goals that I want the robot to be able to go to. You'll see there's kind of a little stick on that side of that goal. That's the heading of the robot. So I can get it to go to a certain goal and face a certain direction. I could also say I don't care what direction you are, just go in there. And just get to that physical location. You'll see if I go to advanced areas, there's a lot of different areas that I can add to a map to make sure that the robot always does exactly what I want. I can add one-ways. I can add preferred directions. So like a car, the robot will always drive on the right side or the left side. I can add single robot zones. So it's an area where maybe it's tight, so only one robot can go at a time. I can do speed limits. I can tell it, okay, in a certain area, I can ignore certain lasers. I can have it do kind of a door goal, so it can get to a goal, and then it will wait, have a door open, and then go through. I can also add forbidden areas. So maybe, like I said, this is what it sees as this front table. So if I want to make sure that the robot never goes through here, I can add a zone that essentially says the robot is never allowed to go into that area. Once you add all the features that you want, essentially you'll end up with a map that looks like this. So you can see all of these orange areas, those are my forbidden zones. So I kind of just made a shell around the map saying, okay, anything outside of there, it can't go to. All of those yellow zones are actually what is called a resistive sector. And we usually will put those around walls or just slightly larger than a forbidden zone, just to give the robot a little bit of a buffer. So if it gets too close, it'll kind of push it away. Here, I added 2 positions for my dock, or my 2 docks for my robots. I have my different goals. At the very top, you can see a one-way that's denoted by the 2 arrows. These red sections are single robot zones, so only one robot is allowed there at a time. And then this is a preferred line. So maybe down a corridor or on a certain path, you want it to follow a pretty strict line. I can put in a path that the robot will try to snap to make sure that it's always going to where I want. I can then add the robot to the map. And I can always localize it so that it knows where it's at. So right now it has a localization score of 64%. And essentially that's just saying that 64% of what it sees matches its environment. You'll see if I turn this, it will fluctuate slightly based on the chairs being in a different position or people being in a different position from where it started. The robot is able to navigate with a score of down to 30%. So even if most of its room or most of its map has changed, it's still able to navigate. So once I have a map and I have a robot connected to it, I now am able to send my robot to different goals. Yes. So it actually can change. So the robot basically has different buffer zones. So it has like a front clearance, a side clearance, and a back clearance. So you could say that, oh, I don't care if something's coming behind it that much, so I can extend that back zone. Otherwise, that front zone, it kind of changes depending on how fast the robot is moving. If the robot stopped, it really doesn't care how close you get because it's not doing anything. But if it's going its full speed, if you walk in front of it within a couple feet, it's going to kind of slow down or stop it. That laser that it's using. Oh yeah, the question was basically how close the robot will get to an object before it stops. And yeah, it will depend on the speed as well as where that object is coming from. That laser that the robot is using is a 4-meter area scanner. So it'll actually read out to about 50 feet. So you'll see it reads basically all the way out here. But that 4 meters is its safety rating. So once you get past 4 meters, basically the gap in between the readings of the laser no longer are safety rated. So any path planning or kind of obstacle detection, it's doing up to 4 meters out. One thing you'll see if someone starts walking is that blue line. What that is a feature called dynamic obstacle avoidance. And what it does is it's actually detecting moving objects and it's predicting its path based on its speed and direction to make sure that the robot can kind of navigate and plan around that. This helps prevent it from coming to a situation where a person might be walking sideways, the robot is coming this way. Instead of them hitting and the robot kind of constantly trying to go in front and being beaten out by the person walking, it'll see that person coming and it'll say, okay, I'm just going to go around them instead to avoid any hurdles or any interference. I can send it to different goals. The robot also uses something called ARCL, which stands for Advanced Robot Command Language. And what that is essentially it's the commands that you can give to a robot in order to control it. So if I go to my robot tab and debug, I can basically open this up. And it essentially is using a TCP socket to send and receive commands for the robot. So if I enter in the password for each robot, it will respond with welcome to the server and then give me an entire list of commands for what I can do for this robot. So one command I can do is a go to. So I can say go to standby 1. And you'll see now it's navigating to my standby position. This is something that kind of your management system or whatever you're using to control the robot, whether it's a PLC or a IPC, is essentially going to send to a single robot. The robot also does have an onboard speaker. So you can actually get it to say certain things when it arrives at goals or while it's on its route. You can even play audio files. We have a couple customers that are playing music as it drives up and down the aisles. Hello. And you can send commands to have it say something or play those files. Just to make other operators aware of the robot where it's at. But yes, yep. So the question was, can you define sound zones? So you can have different zones where anytime the robot enters this zone, it's going to play a specific sound. This is pretty common for going around corners to make people aware that a robot is turning. Maybe an operator or someone walking down a path can't see it. You could have the robot play a little chime or something like that. I can also add my docks. You can have multiple docks for one robot or have robots share different docks. There is also a tablet version for Mobile Planner that you can run on iOS or Android, and essentially it will let an operator see the status of all the robots, where they are, send it to goals. But essentially it kind of takes away the setup and settings. It's meant to be more of an operator panel than set and go on a computer is kind of more of that total control. And there's that tablet version. So ARCL is how you would control the robot if you have essentially one robot and you want to send it a specific command. But what if you have a fleet of robots or multiple robots that you want to control or have running around your building? Omron has what is called the fleet manager that essentially does just that. It kind of acts as a traffic cop for the robots. This used to be a physical piece of hardware that was a kind of a server rack computer that you would put into your server to control it. Now they've gone away from that, and now they use a virtual machine. What this does is it kind of just lets companies use hardware that they might be more comfortable with. Maybe their IT department already has a server that's running different virtual machines. They can just add it to that. Or if they don't want a server rack, they can just run it on a standard IPC or an industrial IPC. It just gives you a little more flexibility. You'll actually see back in the back of the room next to Matt, there is a laptop that is running our virtual fleet manager. So that is basically just acting as the traffic cop between these two robots. With this, they can share a map. So if I have 10 robots, instead of if I make a change on one map, I don't have to go in and change that on all of my robots. Instead, I can just have the fleet manager handle that. And when you make one change, it will push that to all of the robots. You can also do the same thing with configuration. A big thing is once you have different toppers on your robots, you can actually tell it what size that topper is and change what the robot considers its physical size. You'll see that ROIC topper overhangs the robot a little bit. We can adjust that so that the robot knows that overhang. So when it turns, it knows the farthest distance between those points, and it can calculate that. That way, it makes sure that if a physical robot could turn, but the topper might not be able to, it's not going to turn and crash into something. But stuff like that, you can have the fleet manager when you change it on one robot, you can have it change it on all of the robots, or maybe you do have one robot that is different from the rest, you can change it on one versus the other. The big advantage of what the fleet manager is going to do is instead of having to send it those ARCL commands to basically say, go to this goal, you can send it jobs. So you can say, I have a pickup at this location and a drop off at this location. You'll send that to the fleet manager, and what it will do is it will actually figure out what robot is the best robot to take that job. Maybe you have two identical robots, but one is fully charged and one is almost dead. It's going to send the one that's fully charged. Or if you have two robots and maybe one is 2 rows away and the other robot is all the way across your warehouse, it's going to send the closest robot. So instead of you having to send a command to an individual robot, essentially you're sending it to just the fleet manager, and it's handling what robot is going to be the best for that situation. It also will handle queuing, or basically 2 robots trying to navigate around each other. It knows where both robots are, so if it sees an intersection coming up, it'll navigate the 2 robots to make sure that they don't just come head to head and crash or stop based on each other. It'll actually redirect them so that you can have kind of smooth movement between them. If you have a robot that has a job that it's doing, and maybe the robot for some reason failed. Maybe someone put something in the path, so it's stuck in a corner or it can't get to where it's supposed to go. It'll redistribute that job to another robot to make sure that that job is complete. It also handles auto docking. So it will know, okay, if a robot finishes a job and its battery is getting low, it might send it to go charge to refill a little bit so that the robot is available the next time and has a job. These robots do have a runtime of around 15 hours with the battery, or with a payload. Yeah, it'll do managed motion. Here you'll kind of see a little picture of that traffic control that it does. The robots use it's a software, but it's more of a firmware, but it's called FlowCore, and it stands for fleet operation workspace. And essentially that is just the background of what the robot's running in order to navigate and control that. The fleet manager uses the same thing. And then mobile planner is essentially just, it really just creates the map and then tells the robot where the goals are and kind of how you want it to get there. But it doesn't control when it goes to there and where it's going. Instead, that is kind of controlled by your upper kind of management system. Again, whether that's a PLC or an IPC. What the Fleet Manager also gives you is this integration toolkit. And we'll talk a little bit more about that in a couple slides. But essentially, it gives you additional methods of being able to receive commands from the robots, receive the status, as well as send commands to the robot. There are also a couple add-ons. We've already talked about CAPS, but one add-on is Flow IQ. And this is essentially just a dashboard that Omron creates for you that will give you status of all your robots. It will show you your uptime per robot, how many jobs you've completed, what's your kind of ratio of completed jobs versus canceled jobs, failed jobs, things like that. You can get all of this information pulled into a PLC without using Flow IQ, but it is an option where it's kind of nicely packaged for you. So going back to that integration toolkit, what it does is essentially it gives you additional methods. So this is what that Fleet Manager used to look like, that server rack. If I want to have my PLC connecting to that, instead of using those ARCL commands through a socket, I now have the option to do it through a server. So I can use Postgres, that the PLC can pull data directly from the Fleet Manager, in order to get all of the jobs, send jobs, get my robot statuses. Or if you're using IPC, you can use a REST API to get all that information if you want to do it that way. And again, you can use ARCL, that advanced robot command language, if you'd like. There also is Rabbit MQTT that gives you another option for communicating to the robot. This is Sysmax Studio. So this is the programming software that Omron uses for their PLCs. Here is the program that I wrote in order to control these different robots. And in this, I'm actually using that Postgres server, or that Postgres database, in order to get all of my information. So here I can see my robot data, what robots I have online, whether they're available or not, as well as being able to see all of my jobs. So I can see the list of my last couple of jobs, what robot was assigned, what was the status of it. And I can use this to control and send those commands to my robot. This PLC is running in the back there. It also has a receiver that we have hooked up to these wireless push buttons that will send an output or send an input to the PLC. So if I jump back to Fleet Manager, if I look at the fleet window, I can see all my jobs here. So when I press this button, it sends a command to the PLC, which then figures out, okay, I'm commanding it to go to my first goal. So then it sends it the job saying to go to goal 1. And it's going to go over there and it's going to pick up that cart. This would be kind of that upper level management system that you would use if you actually wanted to kind of deploy the robots and have them handle routes or where your pickups and drop-offs are without an operator individually calling it each time. You can have operator stations that essentially will just, if an operator presses a button, the robot will be called to that location and so forth. But if you wanted timed routes or anything like that, it will. You would use this. Jumping back to toppers real quick. The robot by itself is essentially just this. It's just a top plate with nothing on it. Essentially, what you want the topper to be is going to depend on your application. So for the LDs and the MDs, these are kind of a lot of the toppers that we'll see. Most commonly, we probably see the ROIC carts, where it has a cart like that, where the robot can attach and detach, drive that to different parts of your warehouse. Again, the cart is kind of just that base part. You can add whatever you'd like to it. You could add a shelf, panels, drawers, kind of whatever you need for your application. There are, using the onboard I/O and power, you can also add roller conveyors or just a plain conveyor. You could have the robot pull up to a conveyor, index both of them to pull a box onto the robot to move it over to a different side of your warehouse. They also have lifters available for pallets. So the robot will go underneath a pallet and then essentially lift it up off of a stand and then use that to move the robot around. The HDs essentially have kind of the same options, except for the carts. They're mainly used for just lifts or powered conveyors. Sometimes we might even see people put an Omron collaborative robot on top of it. This is what Omron calls a MoMA, or a mobile manipulator. And essentially, this robot will drive to different parts of your building, and then once it gets to a location, the collaborative robot will take over, and maybe it'll do machine tending, or maybe it'll pick parts and put them onto a tray, or pick parts from a shelf and pull them onto the robot. And then, like I said, the most common one that we see is probably going to be the ROIC carts. So we have an LD90, but with the ROIC topper, it actually takes a lot of the weight off of the actual robot itself and puts it onto the casters of the cart. Because of this, we're able to increase the payload. So our LD90 now has a payload of up to 130 kilograms. And the same thing with the LD250, it now has a max payload of 500 kilograms. So it increases the payload, doubles it on the 250 to allow you to handle larger pallets or something that you might not be able to handle with the LD alone. In terms of support and training that we offer here at Mechatronic Solutions, we have 5 application engineers that are located 4 here in this building and 1 in Madison, Wisconsin, that handle all of our products, handle the LDs, and are able to help with any applications, as well as Kurt Thurn from Omron, who is their robotics supervisor, to help with any applications. For trainings, there are also a level 1 training that goes over kind of the in and out of mobile planner, setting up your robot, creating a map, and the different features that you can put into the map. Omron has the option to do that in person or online using their simulators. So you'll connect to a virtual fleet and be able to create maps and navigate the robots that way if you can't make it in person. And then there also is a level 2 integration training that will go into the deeper kind of PLC or upper management side of it. It'll show you kind of the in and out of that integration toolkit to help you kind of figure out how you want to control the robots, what method you want to use, and what commands you have available. Any questions? Yeah, so if I go into, oh yeah, the question was what kind of metrics can you pull from the robot? If I go into Mobile Planner, next to my Jobs tab, you'll actually see a statistics. So here are some of the statistics that you can pull. If you're using those integration toolkits, or that Flow IQ, there's actually a couple more that you can pull than just what's listed in Mobile Planner. But job count, I can see, okay, what is my completed number of jobs? What about job segments? I can have a job that maybe it has 10 different pickup locations and then one drop off location. Those 10 different goals is going to be a job segment. I can see, okay, how many of those jobs have been completed? How many have been canceled? How many have I had to modify? Stuff like that. I can see queuing information. I can see my queue size, my average job age. So maybe how long is a job taken a robot to complete, stuff like that. I can see trips as well as kind of just the status of the robot, like maybe my average parking time or the average distance that it travels per job, stuff like that.
So some of these come from like just inquisitive things or past history. One is you're deploying a fleet of, let's say, like 3 or more mobile robots, and a lot of them are sharing the same job load, but at an infrequent consistency. Is there a good way to constantly cycle behind them, or are you always going to ping the first most readily available robot and burn that one out? The other two get.
Essentially, yeah. If you have 3 robots in a fleet and you're sending it kind of a steady stream of jobs, but maybe just one after another instead of 3 in a row, is it going to send one robot over and over again, or is it going to kind of cycle through the different robots? The robots actually have what's called kind of like an idle time to ready. So once it completes a job, you could say that I don't want that robot to be available again for another couple minutes or maybe 30 seconds. So you could use that to make sure that it's essentially cycling between robots. But by default, it's going to kind of just pick whatever robot the fleet manager thinks is going to be the best robot for that choice. If they're all in the exact same location with the same state of charge, it might pick any one of them. But if that one robot completes a job and then that same job is there and it's the closest one and it has enough charge, it's going to probably just send that robot over and over again. You can kind of manipulate that and send it different commands in order to say, okay, that robot is going to go charge instead, or that robot is just unavailable for a little bit to cycle through.
The other one was partially about open space and acuity, which was partially answered, I think, during the presentation. But I wanted to ask a clarifying question about how it's able to use the lights to help contain that. Is it mapping upward, and thus there's a possible limit of there's like a high clearance ceiling, or is it looking at like density of light that you would see for like a convex and 2 different lights intersect?
Yeah. So the question was how acuity works and whether it's looking for kind of a specific density of light, or if it's looking at the actual light fixtures. The acuity will actually look, and you basically train it on the lights in your building. So as it's driving around, it's basically taking that data from the encoders and the LiDAR, but it's also pairing it with the camera data. But essentially what it's looking for is the actual kind of light signature from your light fixtures. And it's using that basically as just in addition to help it navigate in case the main LiDAR might lose its localization.
Yeah. The second one is kind of based on that is there any kind of path prediction or anticipation where after 1 or 2 cycles, it might be able to learn those patterns ahead of time? Like if it has numerous a particularly difficult hallway to go through or something like that, is it something where after repeat passes through it, they will remember or solve it?
Yeah, is the robot going to learn on a difficult corner, and basically the next time it goes to that, is it going to kind of correct itself? The answer is no, it's not going to remember that data or kind of how it handled that corner the last time. Every time it goes there, it's basically just going to use the features on the map. So what is pretty typical is when you're first getting the robots up and running and deployed, you'll kind of walk around with the robot and maybe see trouble points or see a corner that it might constantly get stuck on. And then you'll adjust the map to kind of get rid of that headache. So if it's turning a corner a little too tight and then it's getting close to an edge or a pillar and kind of stopping itself, you might just put a little bit of a restricted zone on that pillar to kind of push it away from that wall a little bit. Or maybe if it likes to go down this path, but it tends to hug one side over the other, I might just put a preferred line in the middle. But it's more on the map to kind of correct for those changes versus the robot memorizing that.
One is the other follow-up that I have about acuity and pathing and all that. And this isn't from anyone, this is just kind of me being curious during the presentation. If you have like particularly open space, and from what I've heard from other people talking about similar deployments, what they'll do is they'll put physical landmarks along the way in order for it to map those, and it can have difficulties with other foot traffic or vehicular traffic like forklift. Would you be able to, instead of having a physical landmark, utilize the apps tape as a way to landmark for that? That way you have a lower footprints, and if so, does it have the kind of rugged nature to stand for a long time?
Yeah, so could you use HAPS and that magnetic tape instead of using acuity or putting down like physical barriers? The physical barriers are probably what we see the most often, where maybe on a forklift lane, you might have kind of rails on the side, and the robot can just see those as navigation. That's pretty common if you have an area that, yeah, you might only have the pillars as a spot to localize the robot. But yes, the robot can also use the HAPS tape to essentially do that itself. Once it gets onto the tape, so it would still need kind of its enough reference points to be able to find the start of that tape. But once it's on it, it'll essentially kind of just follow that line using both the tape and the encoders, even if it doesn't have a reference point.
Lifeline that it would have without reading it? And are there any like failure points that are common that
Yeah, what does like maintenance look like on the robots, kind of and failure points? One thing that we recommend is some people might not want to have the robot just sit in charge for a couple hours if it dies. Maybe they're running one robot for 3 shifts and they don't have that downtime. They might actually just buy a second or third battery, and then every shift they just swap out a fully charged battery and then charge the other one while the robot's moving around. If you have a battery, we recommend making sure that those don't just sit on a shelf. If you do buy spares or anything, making sure they actually get charged because they're smart batteries, it just helps maintain the life of it. On the actual robot itself, your most common wear item is probably actually going to be the wheels or the tires. The rubber on them will kind of just start to degrade over time just from constantly driving around. Yes. So does it have notification capabilities? Again, one of the big things for Mobile Planner is that essentially it's really just the map and how the robot navigates. The notifications would be kind of more on that management side, but you can have the PLC check for robot faults or see if it failed on a job, and then you can have that email out to a maintenance crew or stuff like that. In terms of smaller notifications, stuff like that, like if it failed going to a route, all of that stuff you could see from Mobile Planner, and basically just read the status that it says. Or you could have, if it fails, like give you a little like pop up. But kind of the more upper level way to do it would be to have that PLC kind of read those statuses for you and then send notifications or emails based on that.
The first is, what's the life expectancy of battery?
Yeah, the life expectancy on the battery, I was gonna say, I wanted to say 5 years. So yeah, 5 to 7 years on it. I don't know the number of like recharge cycles off the top of my head.
Second one.
Yeah, so can you use Omron with another mobile robot, essentially? The fleet manager and the robot itself is not going to be able to talk to that other robot or see its navigation or anything like that. You can have a PLC that controls both Omron and another mobile robot, but in terms of what the Omron robot is going to see, is it's going to view that other robot essentially as just a moving person. It's going to see it as just an object that's moving. It's going to treat it like a person kind of walking along that path. So it'll see it and it'll still do that dynamic obstacle detection. But what you're not going to get is kind of that fleet management motion control, where if two robots are trying to go down the same path, it's not going to say, okay, have this robot sit and wait at this goal while this robot passes and then go. Or if they're coming head to head, it's not going to just seamlessly pass each other. It's going to treat it more as just kind of a person walking in its way because it doesn't have any of that data coming back from the robot. Whereas even if these two robots are on completely opposite ends of the warehouse, this robot is essentially going to know where that robot is going and what path it's taking and be able to plan against that. On the LDs, it's 10 amps. Yep, and it's 24 volts. The battery is a 48 volt. Otherwise, if you need more power than that, say to add a collaborative robot or something like that, typically we might see an additional battery put on top. I believe the MDs and HDs have a higher output, but off the top of my head, I'm not sure what that is. Yeah, so how the robot localizes, as it navigates, it'll actually relocalize. So even if I localize it to a point and I say the robot's here and my localization score is 40%, it's not going to just for the next 2 years be running around your robot or your floor with a localization score of 40%. As it moves, and you kind of saw that when I turn it, it's kind of readjusting itself based on what it sees from the LiDAR. So as it's moving, it's using those encoders as well as that LiDAR and basically correcting itself. So you might start at 40%, and then as it drives down a hallway, once you get to the end, it might be at 90%. So it does relocalize itself. If you do drop too low, the robot might say that it is lost, and then it would require an operator to basically relocalize it. Maybe that's rolling it and pointing it towards a corner or something that I can kind of reference and then relocalizing it to that goal. For different floors, essentially what you would have is if I had 2 floors, I would have this map, and then I would have a map kind of placed next to it. And what it would do is I would have a kind of a macro that runs when I get in. I would have a goal in the elevator. And once I get into that elevator, I would have a macro that runs that basically just says localize to this point over here. And essentially it's just kind of jumping or teleporting it from one map to the other.
Before, like, if Omron is working and suddenly lost Wi-Fi.
Yeah. Yeah, that's a really good question. What happens to the robot if it loses your Wi-Fi network? The actual goals and the job that the robot is getting sent actually gets pushed to the robot itself. So if you give it a job and it's navigating and maybe it has to go down a hallway where it loses signal, it'll continue and it still has that map saved on the robot. It knows where it's going and it can finish that job. The only thing it can't do without a network is once it finishes that job, it essentially won't be able to receive another job because it doesn't know what jobs are coming in. But if you have it lose signal, you could have it finish that job, and then if it's sitting idle for too long, you can have it move to a idle point. So maybe it goes back to a known spot that the signal is better, or maybe it just goes to charge, and then once the network comes back online or it reconnects, it'll then be able to accept jobs. But basically, when it loses the network, it'll finish its job, but the fleet manager will just no longer see that robot, so it considers it unavailable. So it'll send all the jobs to the other robots in your fleet. Yeah. So even with like the lights off or like a low light environment, that laser, that low laser and LiDAR will still be able to navigate. But yeah, if there's a full power outage with no network, essentially you just won't be able to send it a command. If you wanted to, you could plug a laptop into that maintenance port on the side and tell it to go to locations. But yeah. Yeah. But yeah, the robots are really resilient if you do lose network or if it's in a challenging environment. Not natively, no. So basically, if for connecting to emergency systems, say your building has a fire alarm or something like that, the robot's not able to negotiate with your fire system, but maybe your PLC does. So instead, your PLC would kind of handle that, and then if it gets that signal from your fire alarm, it maybe sends the command to send all the robots to a different location or to move them out of the way, or yeah. Yeah, so how large of a map can you have on the robots? It depends on a lot of different features or a lot of different factors. Um, Essentially, when you add different maps or different floors, it will essentially draw kind of like a bounding box from one corner to the next, and anything inside that rectangle it considers as part of the map. So if you have a ton of different floors, like 8 floors, 10 floors, or something like that, you will want to kind of create the smallest box you can, just keep the maps close together in order to just keep that map smaller. The actual max size, I'd have to check, but I believe with the virtual fleet manager, and depending on what your IPC hardware is for that, I think you can do 50. I'd have to check. There's a certain square footage allowable, but we've done kind of multiple floors of big warehouses. You can also delete any data that you might not need. So if you're never gonna go into an area over here, you might delete some of that in order to just save space, stuff like that. Yeah, with the fleet manager, you are able to get larger maps than we could in the past. Yeah, so if there's wood chips on the floor or anything, that low laser can pick it up. It kind of depends on the object size. If they're really small particles, it might not see that as something that kind of is gonna hinder the robot, and it might just try to drive over it. But larger objects, it'll see that and it'll move around it. No, it shouldn't. Yeah, it should be able to drive over it. Yep. Yeah. There is also, I didn't mention, but there is an option for like ESD skins on the robot. Essentially, it's kind of just like a skin that goes over the panels if you do have an environment that needs ESD. The robot wheels themselves are ESD on the robot. Yeah, so if a forklift is coming and it can't go around it, essentially it's going to do a couple of things. The first thing it's going to do is if it's in a hallway where it can't really like turn or anything, and a forklift is coming directly at it, the first thing it's going to do is just look for other paths. It's going to say, okay, I can no longer go straight. What about behind me? Can I go that way and then go down a different hallway and then get to my location? If it can, it'll try that path, but it's going to say, okay, well, I'm facing this way. I need to turn around based on what my physical robot size. Do I have enough space to turn around? If not, it's not going to see that as a valid path. And then if there's no way around that forklift, it's essentially going to fail that job. And then you would either have to manually move it, or if the forklift leaves, the robot will then try again. Yep. There is a brake release button, so if the robot ever is in the way of something, you can hit the e-stop and that brake release, manually move it, and then restart it. And then that on button will actually also act as a continue button. So if it was in the middle of running a job, it's not just going to stop and kind of be lost and just sit there. It'll remember that, okay, I still need to go to that pickup, and it'll resume itself. No, there's no way for the robot to kind of see the forklift in Mobile Planner as it would like a robot. Instead, kind of like with a different mobile robot, it's essentially just going to see it as a moving obstacle. Yep. But no, the only thing that can really you can pull into Mobile Planner is that LiDAR data from the robots.
Maybe there's like a spot that it could go into until the passes, and then
Yeah. Yep. Yeah. So if your path is blocked, you can have it go to kind of different like waiting points until it can navigate. That's pretty common, especially for like skinny hallways like that. Mainly if you have two robots coming, you'll say, okay, I need to make sure that this is clear before I can go. Yep. Any other questions? Otherwise, we're going to run the robots kind of just around. You can see how they navigate together. Feel free to walk in front of it, jump in front of it, see how it reacts. Yeah. Oh, I want to say if I look, what is the water resistance level of the robots? I thought that one of these mentioned it. Oh, for the MDs, it mentions IP22. I'm not sure if that carries over for the LDs or not. No. Yep. Yep. But yeah. Yep. And then even with that encoder slippage, it still is using kind of both that encoder and the LiDAR, so it will readjust itself. No, there's basically just the standard wheel. I'd have to look at what their operating range is. I'm not sure what the kind of the extremes are. And then one thing I should mention is the top speed of the robots. So the smaller robots, like the 90, that has a top speed of 1.3 meters per second. The HDs and MDs, I believe, can go up to 1.8. The 250, I think, is 1.2. And then I'd have to check what the 90 is, or what the 60 is. Any other questions? Thank you guys for coming. That's all we got for the presentation. Like I said, feel free to interact with the robots, see how they handle it. And if you come up with any questions, let us know.